So we're going to do a short introduction to FoodSense, including the analytes that can be detected, the application of FoodSense in foods, the validation of FoodSense. How do we know that this scientifically basically works? We'll do a demonstration. In a bit, I will demonstrate the technology itself, and then we'll do some Q&As at the moment. So what I will do first of all is, so we have a quick agenda. So I'll just go through some slides, and then we'll do a demonstration as well. So welcome to FoodSense. This is a chemical sensor, but it's also a biology sensor for food analysis, quality control, and food safety. So on the next slide, I just want to very quickly just introduce myself. If you're wondering who's speaking today, my name is Martin Peacock. I'm a chemist by training. I have a PhD in electrochemistry. If anyone in your family has diabetes and they have a blood glucose meter, then electrochemistry is the technology behind that. I've worked in industry, and now I run Zimmer Peacock. The company is, we're very strong in the US, UK, Norway, and Indonesia. This company was founded in 2014. We've got offices all around the world. I'm not going to dwell on this because I'd rather speak to you about the technology itself. Just to say, when we launched this technology, it was basically, saying, how is it that people can test their blood glucose quite readily at home? If they have diabetes and they want to control their blood glucose, it's quite easy to do it at home. And yet, if you're in a food industry or food production industry and you want to measure the hotness of chili, it's actually quite a difficult task. And so when you look at the technology, you'll see it looks awfully like a glucose strip. We have a meter and we have sensors. I made this slide last night, but what this slide is, it's a picture of my hand holding my smartphone, and you can basically see that we have an app and we have a meter. The app resides on the iPhone, for example, and then the app Bluetooth connects to a meter, and it's the meter that does the actual analysis and then sends the results back to the smartphone. So if you download this app, and you can download it off the App Store, then there's buttons, and you can see that we have chili. So we measure the capsaicin in chili. We can measure the diallyl disulfide in garlic, and that gives garlic its pungency. There's a molecule called sulfur dioxide, which is often used in food preservatives. I think even shrimp is preserved with this. But it's also used in white wine, so we can detect sulfur dioxide and its derivative, which is called sulfite in white wine. Ginger, the pungency of ginger is due to a molecule called gingerol, so we can measure the gingerol in ginger. And then we can measure pH. pH was quite straightforward for us, and we realized it's probably one of the most measured parameters in the world. We can measure curcumin in turmeric, vanilla aldehyde in vanilla, and then E. coli. We measure the bacteria E. coli in food. I mean, every couple of years you have a press release, or somebody somewhere has unfortunately had food poisoning or had poisoning from E. coli, and they sort of trace it back to, unfortunately, some contaminated water or something that was used in the food processing. So we're trying to mitigate that risk. So the next slide, I just want to kind of give you the idea that we're talking about a little meter that fits in my hand, and we'll show that to you. We're also talking about an app. So we have an app and a meter. If you were normally going to measure things like gingerol in ginger or curcumin in turmeric, or you were normally going to measure vanilla aldehyde in vanilla, you would use techniques like HPLC and GCMS, high pressure liquid chromatography, and gas chromatography mass spec. So HPLC and GC mass spec. The reason I put this slide up here is to say, if you weren't using the FoodSense and you wanted to know the hotness of your chili, then your best option is actually high pressure liquid chromatography. And there is a method which we'll discuss called AOAC, or by AOAC. But it's a really convoluted method, and I think it will, I think the HPLC run alone takes 20 minutes. I mean, to run an HPLC, you need a lab, you need a very good, trained technician, and then you need to interpret the results. It's not easy, and it's very similar to GC mass spec. I'd actually, run both instruments. I actually think the GC is a little tougher. I'm sure some of you out there are really good with these instruments, but there's one final problem, which is they're quite big and they're quite expensive. So I'm just kind of saying, if you weren't to use this technology, then you would have to use HPLC or GC mass spec. You can do sulfite by titration, so that's a little simpler. HPLC, I know that everyone could do HPLC, and then E. coli is often done in a 3-day test. So, somebody takes a sample, somebody sends a sample to their laboratory grows up these bacteria, and then they literally count the bacteria. So what it says is, if you looked at the previous slide, we're able to do equivalents of HPLC, titration, pH, and bacteria counting all from one device. So rather than having all of these devices throughout your laboratory, you're basically using your smartphone and a little meter. We obviously have a roadmap for this technology. Today we can do capsaicin, which is in the chilies. Today we can do diallyl disulfide, which is in the garlic. We can do sulfite, which is the food preservative. We specifically do it for wine. We can do pH. We can do E. coli. We can also do gingerol, which is on this list. We can also do curcumin, which is in turmeric. We can also do vanilla aldehyde, which is in vanilla. And then we have a list of other molecules or other analytes that we're going to bring to this one. And I would say, if anyone's at university or is part of a university, and you've got an interesting test for something like aflatoxin or something like that, then contact us at Zimmer Peacock, or contact Hasim and his team, and let us know about it, because there is a possibility that we could move those analytes onto the FoodSense platform. So we have what we can do today, and we also have a vision for what we want to do in the future. So now I'm going to dig a little bit deeper and say, that we have this app, and you can choose, am I going to do chili or am I going to do E. coli? So I want to just focus in on E. coli first of all. So E. coli. Okay, so the normal workflow is, for example, I'm a lettuce grower, and I know I'll talk about the UK because that's where I'm currently, that's where I live. So, I'm a lettuce grower in the UK. I harvest the lettuce, and then I wash the lettuce. Now, what has happened in the past is that people have washed the lettuce with water that's contained E. coli. So it is a known problem, that E. coli getting into the food chain can be a real problem. So what we've done is we've had to validate. So our statement is this: rather than somebody collecting a sample, sending that sample to the lab doing the test, and then the results coming back, what's generally happening with that is it takes about 3 days. And I think 3 days is actually, I think it actually takes longer than that in reality. So what's happening is food producers are, they're producing food, and I'm sure they're producing it in a very clean, sterile, or hygienic environment. But on occasions, E. coli does get into the food chain. Now that food is being shipped, And retrospectively, people are receiving their E. coli results, and they might actually have to withcall or withdraw the food because actually they discover that there's E. coli. So they ship the food. 3 days later, they get the results, and they're like, "Oh my goodness, we had E. coli," and then there's a real problem there. So, for example, that kind of problem in the UK can cost £250,000 to fix. So it's £250,000, euros or dollars. These are big problems. Anyway, what we've done is, rather than it taking 3 days, we can do a 30-minute test using the FoodSense. Now, we prepare the food in exactly the same way as, or prepare the sample exactly the same way as the current standard, which is an ISO standard. In the ISO standard, they then put the sample onto a gel plate or an agar plate, and they let the bacteria multiply, and then they physically look at this, what's called a Petri dish, and they count it. I appreciate a lot of you are in, this kind of industry, so you understand what I'm saying. But they prepare the sample in accordance with an ISO standard. They put it on the Petri dish. They then count it. Now with FoodSense, what you do is you actually put the sample on our little sensor. One of the guys who's on the line, if you just mute yourself. They put the sample on the sensor, and they get a result in 30 minutes, which is a lot quicker. Now, what we've done is we've actually compared ourselves versus the standard method. So the standard method is to do this ISO standard. You put the sample onto the plate, and then you count how many colonies do I have. So in this example, the sample had 692 CFU, colony forming units. In this sample, they had 596 colony forming units. In this example, they had 880 colony forming units. And then we've also then done the same sample on the FoodSense. So we've got 645 versus 692. So it's a difference of about 7%. We've done the comparison again. We've got a difference of about 8.2%. Here, it's actually a difference of 0.5%, and here's a difference of 0.3%. So what it says to you is, that here's the standard classic method, which takes 3 days, and here's the 30-minute method, and these two things compare very well. So now, if you're a food producer, rather than having to send food out effectively untested, it can be tested very quickly within 30 minutes. Then the safety officer or the quality officer can say, okay, we understand that, and then they can ship the food. So I said that I would talk about how we've gone away and validated E. coli and chili. So to summarize E. coli, we took 5 samples, for example, and we did it exactly the way it's done today, which is agar plates, growing bacteria, and literally counting them. And then we also did the FoodSense method, and the FoodSense app will give you what's called the CFU per mil, colony forming units per mil, and we compared and validated to make sure that we were in, we wanted to be within 10% of the real, not the real, but the standard method of doing it. So that I started with E. coli. Now I want to go on to, so E. coli is obviously food safety. And we really started this journey with something with food quality. So I'm going to talk about capsaicin. It's a molecule close to our heart. I'm sure this is, again, known to many people. It's a molecule that gives you the perception of hotness. Now, before the FoodSense came along, the way you could measure hotness in food was, I mentioned an analytical method earlier on called HPLC, high pressure liquid chromatography. That's one way of measuring capsaicin, and from there you can calculate the Scoville heat units. The other way of measuring the hotness of a food and reporting it in Scoville heat units is the panel test, where you get a group of people together, you do dilution, dilution, dilution. You keep on diluting the sample until you can no longer taste it. I don't really think this is going on very much because actually it involves a lot of people. It has to be done correctly. People can only do a few samples a day before they can no longer detect, or they can no longer sense the heat. I think I say here guessing. I mean, really what's happening in food production is, the head of quality will, taste it and say it tastes right. And now what's happening is, I met one person and their problem was this, that they had tasted the foods and they said, yeah, it's correct. And then the supermarket had said, no, it's not, it's hotter. And so they're in a situation where you've got a person, who's like selling the food and a person who's produced the food, and the one saying it's hotter and the other one saying, no, it's not. And there is no data to back that, conversation up, or to back up, your side of the story, let's say. But the FoodSense, I'll do a demonstration of the FoodSense as part of this today. The FoodSense allows you to do this very quickly, within about 3 minutes. So at least then you have the Scoville heat units. Now we've had to validate, obviously, this method. So there's an AOAC method called 995.03. It's an HPLC method, so it's a high pressure liquid chromatography method, where you take the sample, you extract the sample, you dilute the sample, you put the sample on the onto the instrument, and then the instrument does about a 20-minute analysis, and you won't get a result back, you'll get a peak back. And then you will look at the height of the peak and you will say, from the height of the peak, I will calculate how much capsaicin is in that sample. And from there, you will know how much capsaicin. You can then convert it into Scoville heat units, and then you can report it. For example, to do that kind of testing in Europe, costs $100 at least to do, and it really takes a couple of days to get the result back. With this technology, it's the same as the E. coli, but rather than the E. coli does take 30 minutes, this takes about 3 minutes to do. So you get a result back very quickly and much, much simpler than trying to do an HPLC method. In order to validate it, it's very important. When we validated the E. coli, we did the traditional way of testing. We put it on an agar plate, we put the sample on an agar plate, we grew the bacteria and we counted them. And that's the traditional way of doing it. For example, trying to measure the hotness of chilies, we did the HPLC method, the AOAC method. We have an HPLC in our facility. I think it's by either Waters or Agilent, but these are the two big sort of manufacturers. We did the HPLC method. We got the concentration of capsaicin from HPLC, and then we checked our FoodSense against it to make sure that we were correlated well with the HPLC method. Because what often happens is people have been testing their samples for years by HPLC, and so when they get the FoodSense, it's important that we are able to demonstrate a correlation with their traditional way of testing. It is very interesting that when you start testing people's products and you tell them what the Scoville heat units are, they're always like very defensive because people think, oh, my product is hotter or cooler than it really is. But of course, that's a subjective experience. If people have been using tasting as a quality control for years, to sort of, you can't deny their subjective experience. When they taste it, you can't deny their experience. But if you objectively measure the capsaicin, it might be different to what they're actually expecting. So we do get into interesting discussions about, well, this is hotter than that, but actually the capsaicin levels may not say that. The perception might be somewhat different. I just want to give you a history on this. I am conscious that we don't have all the time in the world, but I just want to give you a quick history. Where does this technology come from? Why are we speaking here today? And so the next slide, there's a few things on the slide. We have a picture of Harry Potter, obviously, a picture of some chilies, and then a picture of Oxford University. So if Oxford University looks familiar to you, you've either visited it, you've seen it in pictures, or if you've ever watched Harry Potter, then that Hogwarts is often filmed at Oxford. So Oxford is like walking around the film plot or the film set of Harry Potter. Anyway, so the backstory here is this technology originally came from Oxford University in the United Kingdom. There's a professor there called Professor Richard Compton. I'm very much hoping to get him to come on a sort of tour of Southeast Asia with me. He's a very good guy, a very eminent electrochemist, and he originally invented the technology around E. coli and chili. So I'll talk about it in a minute, but he's an electrochemist. He uses technology called cyclovoltammetry, and that's the technology that's at the heart of what we actually do. So in chili, there's actually a molecule called capsaicin. This is the guy that is often used to kind of account for the hotness of chili. And the technique of cyclic voltammetry is I know it's a very electrochemical technique, but it basically involves applying increasing amounts of voltage to a sample and watching the current change as the voltage changes. So I know, I know that there's a lot of science in that term, but cyclovoltammetry, you increase or change the voltage, and as you change it, there's a different current. So when you look at my axes, we have a potential on the x-axis and current on the y-axis, and there's a very distinctive shape if you look at that, and that distinctive shape is a fingerprint. It tells us, that there's a molecule in there, and it has a fingerprint, and that fingerprint is identifiable as capsaicin. Now, you can see we've got some peaks in there. There's a peak, and that peak height is proportional to the capsaicin in the sample. So we have the ability to both fingerprint the sample and say, is it capsaicin? But then we also have the ability to do the peak height. And it's really important to realize that we don't then display this raw data to you. We actually interpret the data and give you the Scoville heat unit. So we have a calibration within the instrument that looks at this peak height. It checks that the profile is, let's say, correct, and then it will report the Scoville heat unit to you. So Richard Compton at the University of Oxford was the inventor. If you ever read his first scientific paper on this, you'll see him use a technique called cyclovoltammetry. Capsaicin is electrochemically active, and it gives very distinctive peaks in the cyclovoltammetry, and those can be used to identify that the sample really is capsaicin. And then the peak height tells us how much capsaicin is in the sample. And so when we run the test, it's we convert this raw signal into Scoville heat units, which is more meaningful to people in the industry. So I do a little bit of discussion about what's actually happening in the cyclovoltammetry. And I'm sorry, I am at the beginning of the talk, I said I'm an electrochemist. So, therefore I like to talk about oxidation and reduction of molecules. But what's happening is the capsaicin is oxidized, and it gives us a very distinct peak. The peak is proportional to how much capsaicin is actually in the sample. I did say that we'd obviously validated this test. So, to validate it, we went out there and bought a range of powders, a range of chilies themselves, a range of sauces, a range of things like oils, so that we could test all these different types of samples, and and then also check them on the HPLC, on the high pressure liquid chromatography, using the AOAC method, and make sure that we were correlated between these two things. And as I say, we do not give people the score of capsaicin in what we call micromoles. So I'm a chemist as well, so I like to deal with micromoles. We actually convert the score into Scoville heat units. And I'll show you that in the demonstration in a short while. So I've moved to another part of my home office. I've had to change cameras slightly, so it's nice to speak to you guys again. What I'm going to do is I'm going to change angles on that camera and come down and show you something down here. So now hopefully you can see my, you can sort of see my hands if I put my hands into the shot. So I want to describe to you what we've actually got here. So earlier on I was talking about, we had an app, and we do have an app, and for example you can do chili, garlic, vanilla, E. coli. Now at the moment this app, it says hardware connected, so it's in Bluetooth communication with the FoodSense meter, which is here. So I suppose if I put my finger in, you get a sense of how big or how small it is. So we have an app in Bluetooth communication. So this FoodSense meter will be told by the app what to do. So the next thing I'm going to do is I'm just going to get some chili sauce out. One of the interesting things is we've done so much testing of chili over the years now. That you can almost tell the hotness of chili sauces sometimes. I mean, as this bottle browns and darkens, it's basically oxidizing. The capsaicin is oxidizing, and it does become less hot, and you can see it in the result because the Scoville heat units go down. So what I'm going to do now is, what we do is, sometimes people give us oils, sometimes people give us sometimes people give it oil, powders, sauces, maybe just the berries themselves. So we often like to dilute the sample so that we can basically sort of fix the matrix and make sure that you can't just test the powder. You have to suspend that powder. You can't just test an oil. You have to sort of put some water into the oil so that we can, in order to test it. So what I've done here is I put down 4 drops of we call it chili pot buffer. It's a buffer that we ship with the unit. It's probably worth saying we actually ship the pipette as well, so we're not expecting, we do ship the pipette, we ship the buffer. We're trying to make sure that you've got everything you need in order to just kind of open the box and get going, and that you didn't get a surprise. So that's what we're working on, or that's what we do rather. So the next thing I'll do is just taking up the sample. Right, so I've basically taken 4 drops of a buffer, 1 drop of the sample, and now I'll mix it together. Sometimes, in fact, I do actually use a vortexer to really get this homogenized, really get it really well mixed. Admittedly, I'm doing it just sort of by hand, like this. But yeah, if I want to get a really precise or repeatable answer, then I do actually use a vortexer. But I've kind of prepared the sample there. Now, it wasn't necessarily very clear in my presentation, but we use sensors. This is an electrochemical sensor, and for the chili, there's a chili sensor. For the garlic, there's a garlic sensor. For the E. coli, there's an E. coli sensor. There's a different sensor for each analyte. It's really important because you don't really want to mix them up. I said that this was a bit like a glucose meter for diabetics, and so the sensor pushes into the front like that. And what I'll do is now I'll put the sample on. What I'm going to do is I'm just going to put, I think, approximately 50 microliters on the tip of this, and which I've done. As I say, this is actually 100 microliter, but I've left some of the material actually in the tip. So I've done that. So I've taken 1 volume of the product, mixed it with 4 volumes of the buffer, mixed it, put it on a sensor. Now the app, I've done a 1:4 dilution, so the app knows that, and it will recalculate the Scoville heat units of the product rather than the diluted product. And then I hit measure, and now it's measuring, and so now it's sort of, there's a little progress bar trundling away here. Right, let's summarize the talk so far. All right, so we're Zimmer and Peacock. We're developers of the FoodSense. We work with Hasim and his team in Indonesia, supplying this product and supporting this product. You know, it originally came from the University of Oxford. It was trying to meet a need which was, you know, in order for people to test things like chili and E. coli, it was either very expensive or took a very long time. So it's come back, if you look at the score, at, I'll try and hold it up now, 5,005 Scoville heat units. So that's obviously a live demonstration where I prepared it in front of you. And if you ever Google Tabasco sauce on the internet, then you will find that they ship it, or people measure it, they say they ship it between 2,500 and 5,000 Scoville heat units. So you can see that we're practically dead on what they actually claim. So it's a very, very fast method for doing food quality analysis. The alternative to this is an HPLC method. HPLC, depending on which one you buy, can cost you up to £50,000, and the throughput on the HPLC is nowhere as fast as this. So what I'm going to do now is I'm going to just mute this and move over to another computer. I'm just going to start talking to Hasim. So, okay. So I just wanted to give you a verbal summary. Can I ask you, did you see the demonstration okay, Hasim?
Yeah, I think so. But we have some question from probably after you deliver your last statement.
Yeah, sure. So I just want to summarize, you know, that we've obviously, you know, we wanted to finish with a demonstration to show people, you know, live streaming, you know, that, you know, how to do a test. If when you look at the entire webinar, the longest part was the talk. The test itself is very quick, but that's the entire idea, you know, that you shouldn't be waiting an awful long time to get the result. You should be able to just, you know, take a sample, prepare it, put it on the sensor, get a result. So Hasim, we probably do have some questions, and I can see a very good question here. How did you functionalize the electrode surface for the detection of E. coli? And I knew I hadn't said it, and I'd forgotten about that. So I did see a question from Martina asking, how did we functionalize the electrode surface for the detection of E. coli? Hasim, do you want me to answer that?
Yes.
All right. So what I'll do is, and I apologize for that, because I didn't make that very clear. I realized. So what I'll do is, I'm just going to share my screen with seconds, Martina. I'm just going to put in a, let me go to the web and go optimizing a sandwich assay, Zimmer and Peacock. So what we've done is, I know we're getting right into the details for everyone, but this, you know, what we've done is we've taken the electrode, and I think you probably already guessed the answer, but we've taken the electrode and we've put the E. coli antibodies on the surface, so that when the E. coli attaches to the surface, we get what we call a blocking assay. So we will get a signal when there's no E. coli present, and then when the E. coli binds, the signal changes proportionally. So the quick answer to Martina's question is we functionalize the surface with antibodies. We use a blocking assay, but I do appreciate the question because as I was speaking today, I realized I didn't answer that question. Now, and here's an interesting. Hasim, do you want to choose a question for us?
Martin?
Yeah.
Yes, we have another question from Abdullah. From Abdullah from Cambridge University. The question is, I have my own electrochemical sensor design. It's possible if we can manufacture it in very low volume?
So the quick answer is, I know we're here to talk about FoodSense today, but Zimmer and Peacock, we're a contract developer, a contract manufacturer of biosensors and medical devices. We're what they call ISO 13485, which means we're registered or certified to develop medical diagnostics. So the quick answer is yes. We are very good at doing that kind of work. And it's nice to hear from you, Abdullah. I actually live near Cambridge myself, just 12 miles out.
Okay, and what is the minimum we can make it?
I think the minimum we can make it might be, do you think that's a question, or the minimum we can make in terms of sensors?
Yeah, for volume. I don't know, it's not clear about this.
What a difficult question. It all depends on size. I'm a good guy for giving an answer. The minimum is often around about 5,000 sensors. So, it's quite, even our minimum is quite small. But do contact us. What I would say is, if you've got questions like that, go to the Zimmer Peacock website, go to contact and support. Fill in the form quickly. They all come to me anyway. So just say, just put your details. They come to me, and that's a good way of with that conversation.
Okay, I see. For Abdullah, you can send your question to our team, and we will send to Martin. And next question from Indonesia, from Johnny Firdaus. What type of sensor was used in the device? What type of sensor?
So the types of sensors that the type itself are electrochemicals. So the technology is electrochemistry. The sensors are made by a technology called screen printing. So, I'm just saying these keywords so that you can kind of investigate what this means, but we make electrochemical sensors and we screen print. I mean, just for your interest, if you ever go to the Zimmer Peacock website, you will find a whole range of screen printed electrodes. So you go screen printed electrodes, and you will say to yourself, oh, I want a low cost carbon electrode, for example. And then you can find, on our web store, all this information about screen printed electrodes. Now, the type might mean, and then we make, for example, glucose sensors. So if you go to products, biosensors, glucose sensors, lactate sensors, calcium sensors, potassium sensors, ammonium sensors. There's a whole list of sensors. Now, there's also a second part of this answer, which is for the FoodSense, we do chili, garlic, ginger, vanilla, turmeric, pH, and E. coli are the sensors we make for the FoodSense. So if you're in the food industry, then you're very interested in the FoodSense is the right product and technology for you. If you're in academia or want to develop your own technology, then it's going to the Zimmer Peacock website and looking at our either existing sensors. For example, somebody wants to make an alcohol application, or somebody wants to measure glucose in the blood, they can get those kind of sensors here. And we also do the screen printed electrodes, which allow people to develop their own types of sensors. Hasim, what else?
Okay, thank you. Next question is come from Italy, from Veronica and Michelangelo Pascal, about how you build calibration curve, and is calibration prepared in metric or something material, and how about the repeatability of the result from sensor?
Yeah, sure. Okay. So first of all, you know, how do we do the calibration? All right. So, for example, I'll go back to my slides. The original way we did calibration was to do a sort of take capsaicin, put it into buffer, and make sure that our signal is proportional to buffer. I'm sorry, proportional to capsaicin. So if I'm going to talk specifically about the chili. So we take buffer, we put capsaicin, we get a peak height, and we make sure that that's linear. Now, your question's already indicating that you understand the matrix effect, you know, which is, it's one thing to get a calibration curve in a buffer. It's another thing for it to work in a real sample. I actually took the slide out earlier on. So what we did is, first of all, we did scientific experiments in buffer by just putting capsaicin in there. The real way that we actually validated this method was to actually do a correlation between, I think it's here. Yeah, we did a correlation between HPLC and the electrochemistry system. So we took known samples and we tested them by the known method, and then we tested them on our instrument using our calibration and said, you know, are these two instruments giving us the same results? So it's sort of a calibration, but you could also call it a validation or a correlation against the incumbent device. So we calibrated in buffers, but your question touches on matrix. We also then validated or correlated against the HPLC method. And then finally, the matrix effect. So how we get rid of the matrix effect is this. You saw me do a dilution of 1 in 4. So effectively what I'm doing is I'm diluting out the matrix effect. So you are correct. There is obviously a matrix effect. You get a matrix effect when you test blood and you test urine. There's always a matrix effect. And how do we deal with it? We do dilution. And if I find a sample that has a lot of background or a lot of matrix effects, we actually increase the dilution to something like 1 in 10. So we really dilute out the problem. So you're correct. There is a matrix effect. And in part we get rid of it using the HPLC. We get rid of it using dilution rather. I did see an interesting comment on one of the guys was saying, well, you know, E. coli is multifunctional. How do you address cross-reactivity? And what I would say is this, that at the moment, the way to test obviously for E. coli is to go, you know, take a sample, do the workup, put it on an agar plate, and, you know, wait at least 12 hours in order for the colonies to grow. That's the way to do it today. But what I would say about this technology, it's actually a very quick screening technology, because, you know, E. coli contamination, you know, in my opinion, is very rarely just one species. You know, it's a, you know, there's a few E. colis in there. If you've got an E. coli problem, you know, you've generally got a hygiene problem. So there's a mixture of E. colis in there. So what we're good at, I would say, is screening. You know, I want to know in 30 minutes, do I face a high risk of contaminating my food or having contaminated food in my production? Or do I have a low risk? And it will help you answer that question. I'm actually at low risk, or if I find a positive result with this instrument, you know, I'd say you first of all have to do the agar plate. You might start getting into PCR and finding out what the species is, but it's a very quick way of screening. It's a 30-minute test as opposed to a 3-day result, and that's really what that's what we're trying to, not trying. That's what we're telling people. Hasim, do you want to?
Okay, just one last question, I think, because it would be finished now. From Eric Sugero from Indonesia. Is it possible using a sensor for one analyte, or can multi-analyte?
Yeah. No, I understand the question. So, for example, I'm just going to go to our kind of scientific pages. I'm just going to Google credit card Zimmer and Peacock. So I understand the question. So the quick answer is we're doing one analyte at a time. If you're particularly interested, one day maybe it's a research program or it's so the answer to the question is we do one analyte at a time, and we do have on our website technology where we actually demonstrate that you can actually have several sensors in a row. So it's one sample on a microfluidic device, and the sample flows down, and you can then detect it in these different chambers. So that is not a product, that's a research tool. So I understand the question, and the answer to your question is no, we sense one analyte at a time. And if somebody came to us and said, well, look, I want to develop a new diagnostic for food and I want to test all these things in parallel, then we would have to do a development with them, and this would be one way of doing it. This is the size of a credit card, and so you can get a sense, it's quite small, and you can put one sample on there. It splits the sample into, for example, 6 chambers, and then you could do glucose, lactate, pH, sodium, potassium, ammonium, for example. All right, Hasim. So
okay, I think it's clear. Yeah.
Is that good?
Thank you very much for your presentation. It would be useful for our participants. And thanks for your wake up early. I know it's hard for you because actually it's beyond our expectation, because this webinar could be for Asian and Australian, but we have list of participants come from 14 countries, including Argentina, Italy, Belgium, and UK as well. So some European region, they follow the event. Thank you very much. And again, thank you for your presentation.
All right. Well, thank you very much, everyone. Thank you very much for attending, and take care, guys. Thank you, Hasim.